Hey everyone, this is Michael from Bright Musical Circuits. This is the new version of the QTLFO module. And I've also got the schematic for the old one pulled up, and I gave that a yellow background, and the new one is a light blue background. So if I go back and forth, you can kind of see the differences. And I'm going to go over how it works first, and then I'm going to show you the differences between the old one and the new one. So I'm going to start way here on the left with the Schmidt trigger. And this is a inverting Schmidt trigger. We are going to start by pretending that this has a positive output. So we've got positive voltages coming out of here. We've got 3 resistors here that are setting up the threshold and the output of this Schmidt trigger. And we'll go over the input later. This is all a big loop, so we'll come to the input at the end. But we've got a 120K, a 2.2K, and an 82K resistor. This 82K is going to ground. Part of the reason I did this was to make sure that if we have variance on resistor values, if somebody's 120K actually ends up being a 130K, and then their 82K actually ends up being a 78K, that you have that 2.2K in the middle that's acting as giving you a little bit of breathing room. Because if you set the output of one Schmidt trigger so low that it's never going to hit the threshold of the other Schmidt trigger, because these two are feeding into each other, you would have a situation where it would just stop oscillating because you'd never be able to reach it. And so this should make it a lot more stable, and people should have a lot less problems with it just not running at all or it getting stuck on one step. But so yeah, this is a voltage divider with just 3 resistors to it instead of 2. The output is set to 4.7 volts. With the resistor values, I don't want to introduce too many new resistor values than the ones that I normally keep on hand for my sanity, and so people don't have to buy as many values. So I erred on it being a little bit under 5 volts rather than it being a little over if I had gone with just 100K. And yeah, the output of that is being sent to this buffer over here, and I'll zoom out a little bit. So this buffer, the positive input is coming to the output, and then the negative input is monitoring how this capacitor over here is being charged. So the output of this buffer is always going to be kind of the difference between the capacitor and its input. So if this cap was at 0, our output voltage here would be plus 4.7 volts, and we would start to see current flow through this diode here, and then this pair of resistors here. This is a potentiometer that's just set up as a variable resistor, and that's controlling how quickly that capacitor charges up. And then once this charges up to 4.7 volts, the output of the buffer will go down to 0 volts. And I'll just point out now that this is one of the biggest differences, and this is like the thing that made everything else a lot simpler, even though it doesn't seem like a big deal. In the old one, we had the buffer that's charging the capacitor buffer through the diodes. Same deal. The difference was where we got the feedback for the buffer. If we had been connecting it here, the buffer's output would account for diode drop. So there's these diodes here that those are you're going to lose a tiny bit of voltage through there. So because of that, the capacitors would be charging to a smaller voltage. So because of the diode drop, you're going to lose a little bit of voltage on those capacitors. And then that led me to, on the Schmidt trigger, adding these diodes here to account for that diode drop, which complicates things more. It's adding more parts to it, which we don't want to do. And then the more parts you have, the more likely something is to go wrong, that you have a bad diode, or you have a diode that's a little bit out of spec with its voltage drop. So by doing it this way, it really does simplify the whole process. And then another change I made was in the old version, I had these 2 10UFs back to back. And then now it's just a 10UF non-polarized. At the time, the Tata, who is where I buy most of my parts from, they weren't keeping non-polarized caps in stock all the time at the time that I designed the original. So this also lowers part count and also should give us a wider range of lower frequencies. Going back to tracing how this circuit works. So our cap has now fully charged to plus 4.7 volts here. And then that is going to just a regular, a buffer that is being fed back from its output, like a standard buffer. And then that is setting output 1's voltage and feeding this LED here. Another little difference I made is that I changed from a 1K resistor for the LED to a 10K, which will lower the brightness a little bit, but save you on current. That's plus 4.7 here. And then that is going to go to this op amp on the right, which is set up as an inverting gain stage with a gain of 1. So that is just going to take our 4.7 volts and turn it to negative 4.7. And as you can see, it has 200K resistors. So these resistors are another spot where you could have a little bit of variance between the stages, and it could throw off how much gain. Like if this 100K in the feedback was actually a little low, like just like a 90K, that could potentially lower the output voltage here down to a voltage that would be too low to trigger the threshold of the other Schmidt trigger using the old schematic. So it's another spot where it's important to have that tiny little gap between threshold and output. And so the output here of negative 4.7 volts gets fed across this wire. Boop, boop, boop. Keeps going. And all the way down to the input of our other Schmidt trigger. And this one is set up exactly like the other one. So we have negative 4.7 here. And if we had negative 4.6 here, saying this was negative before, that would be enough for it to trigger a change in phase here, which would then change this up to plus 11 something. This becomes plus 4.7. And then this becomes plus 4.6. And we would have a phase change where our capacitor would go from being at negative 4.7 to then it charging through this diode again and going up to plus 4.7. And the outputs are the same for this bottom row as they were for the top row. The only difference being which op amp we do. So there's no inversion before we send it back to the first Schmidt trigger. So we have plus 4.7 here, plus 4.7 here, and that is going to send voltage all the way back to where we first started of going to plus 4.7, which will be enough to then have another phase change and send this to a negative 11. Then this becomes negative 4.7. And then our caps here will then discharge and we will oscillate as we go. Whew. So that's how this works. That's how we have these 4 knobs that are controlling 4 different phases of this in a big feedback loop. I guess I didn't really go over the pots, what the different pots are doing. So when we are raising the voltage here, this is going through this pot marked R1, F3. So that's rise 1, fall 3. So that means the voltage is going up on output 1, and then it's going down on output 3. And that's because output 3 is just an inversion of output 1. And then it's the same thing when it's going negative. That's going to be the fall of output 1 and the rise of output 3. The other thing is how long these stay high or low before they rise or fall is being set by the rise to fall 4 and rise 4 fall 2 pots down here on the bottom. So yeah, every pot is going to affect every output at all times, but it's not always going to be a very noticeable difference. I guess the other difference is I got rid of this 100K pull down resistor. I just took it out. I realized I just didn't need it. It's as simple as that. I wasn't sure if I needed it or not initially, so I included it. And then later on, I just removed it and it kept working. But yeah, thanks very much for watching this video. I hope that helped.